A high-voltage spark jumping across a gap is a violent release of energy. This discharge is rarely a single one-way event. The charge actually behaves with a hidden, rapid complexity. Early electricians stored this immense charge in a device called a Leyden jar, which acts as an electrical condenser or capacitor. When a capacitor discharges, logic suggests the electricity should simply flow from the high-pressure side to the low-pressure side until the voltage reaches zero and then stop. Instead, the current overshoots the 0 point. It empties the capacitor entirely and continues forward, reversing direction and sloshing back and forth in a rapid oscillation. To understand why electricity bounces, we must stop viewing it as a simple fluid draining from a tank. We have to treat the circuit as a mechanical system subject to the laws of classical physics. The components of an electrical circuit operate with the exact same physics as a heavy metallic mass suspended on an elastic spring. By mapping these circuit components to mechanical properties, inductance to mass and capacitance to elasticity, we can predict exactly how electricity will move. This isomorphism was formulated by Sir William Thomson in 1855, proving that these electrical oscillations follow the same mathematical rules as a mechanical pendulum. Mastering electromagnetic resonance requires a shift in perspective, realizing that invisible magnetic and electric fields possess physical inertia and elasticity. Let's start with the wire coil. A steady electric current flowing through this tightly wound copper solenoid creates a steady magnetic field around it. When that current changes, the magnetic field changes with it. This fluctuation induces a counterpressure in the wire, a back electromotive force that actively opposes the change in the current. This property is called self-induction. The opposing voltage equals L, the self-inductance of the coil, multiplied by the time rate of change of the current. In mechanical terms, inductance is exactly equivalent to mass. Just as a heavy physical object resists any sudden change in its velocity, inductance resists any sudden change in the electrical current. The energy required to push current through the coil against this resistance is not lost. It is stored as kinetic energy within the magnetic field itself. An inductor acts as the circuit's momentum. It forces the electricity to keep moving even after the original driving voltage disappears. While the inductor provides momentum, a second component provides the restoring force, charges held at rest inside an electrical condenser. This is a capacitor. Its electrostatic capacity C is its ability to store an electrical charge across an insulating dielectric gap under a given voltage. The voltage across the plates equals the quantity of charge divided by the capacity. A larger capacity means less voltage is required to store a specific quantity of charge. This maps directly to a mechanical spring. The electrical capacity behaves identically to the reciprocal of a spring stiffness. Pushing charges into the capacitor is like physically compressing that spring. The energy is stored as potential energy. A fully charged capacitor is a coiled mechanical spring, holding intense electrical pressure that is ready to be released. Now we combine our spring and our mass into a single closed loop with a spark gap as the trigger. Currently, the system holds maximum potential energy. When the spark gap closes, the resistance drops. The capacitor discharges, pushing current through the coil, just as the released mechanical spring pulls the mass upward. The current hits its maximum exactly when the capacitor is empty and the voltage is zero. Mechanically, the mass hits its peak velocity exactly as the spring passes its resting length. The process doesn't stop. The coil's magnetic field collapses, forcing the current forward and overcharging the capacitor in the reverse direction. The mass's momentum compresses the spring upwards. The cycle reverses, continuously trading electrical potential energy for magnetic kinetic energy. If this system were frictionless, this electromechanical pendulum would slosh back and forth infinitely without ever losing energy. In the real world, wires have resistance. This property acts precisely like mechanical friction or air resistance. Unlike the inductor or capacitor, resistance does not store energy. It permanently consumes it by converting the electricity into heat. This friction dampens the oscillation, stealing energy from every swing until the system comes to rest. How much friction is required to stop the bouncing entirely on the very first swing? Thomson discovered the boundary. The discharge only oscillates if the resistance squared is less than the ratio of 4 times the inductance over the capacity. This equation determines whether the circuit will oscillate. It marks the mathematical boundary between the system's friction and its ratio of momentum to elasticity. We translate this math into a time domain graph to see the current over fractions of a millionth of a second. This is case 1, the damped oscillation. With small resistance, the current draws a decaying sine wave, swinging above and below the zero line. As the resistance increases, the amplitude of these waves flattens out faster as more energy is lost to heat during each cycle. When we reach the point where R squared equals 4L over C, we arrive at the critical case. The current is now critically damped. It rises to a small peak and smoothly returns to zero without ever crossing the axis. The friction is too high to allow a bounce. By tuning these 3 variables, friction, inertia, and elasticity, an engineer can dictate the exact life cycle of an electrical impulse. For circuits designed to ring freely, we can calculate how fast they vibrate. The period of a complete oscillation is given by the formula T equals 2 pi times the square root of L times C. The starting voltage is absent from this equation. The timing relies purely on the interplay of the circuit's electrical inertia and its elasticity. Controlling these oscillations allowed scientists to scale up from laboratory sparks to currents that push energy out into the surrounding medium. The development of wireless telegraphy and modern radio relied on realizing that the invisible movement of electrons perfectly obeys the laws of classical mechanics. Every wireless transmission we rely on today is essentially a highly tuned pendulum, swinging exactly as Thomson predicted over a century ago.